Our next snippet, I'll again probably just do two problems so it's not too long. Problem 7, we've got a ball rolling off of a fixed cylinder. This thing doesn't move. And we just nudge it, get it going, and then it goes faster, faster, faster as gravity does work on it. If you know what, let's go to the free body diagram for this, the center of mass. I've got a normal force, and I've got gravity down, and I also do have force due to friction because it's rolling without slipping. But that force due to friction there's no power. Remember our power, force times velocity, that the point of contact is not moving. There's no power, dissipated by this friction force, and therefore no work over any time. And so we can forget about this. It is there, it is, causing the rolling, but it does no work. So we've got energy conserved. My increase in kinetic energy is minus delta U, so I must have a decrease in delta U, and that's exactly what we expect. The potential energy goes down. And by the way, this all checks with work. The work on M by gravity is positive. Delta K is positive. It's minus the work against gravity. In this case, the work against gravity is negative. Well, the other thing to remember is we can set it and forget it. When we're rolling with a particular body, I've got my translational and my rotational. The moment of inertia here is some beta mr squared. The r squared omega squared is locked into v squared. It's rolling without slipping. So I get 1/2 1 plus beta mv squared. So for a hoop with beta 1, I would get 2 times 1/2. I'd get mv squared as my total kinetic energy everywhere, anywhere it's rolling. The change in potential energy we know is going to be negative. Sure enough, y, the center of mass position, will go down. The final position minus the initial position is the r plus r cosine theta. That's to the center of mass, and then I go over and get the height here. And this is theta in between. So this is little r plus big R. And so this is little r plus big R cosine theta. And then, of course, the initial value was just little r plus big R. So I got big R plus little r cosine theta minus big R plus little r, and that's certainly negative unless theta were 0. And you remember that Newton's second law for the center of mass radially involves the acceleration of the center of mass, so that r that comes into centripetal acceleration is the center of mass position. That's little r plus big R. So that's a familiar thing for us. Oh, I want to tell you something. We could have, when we were talking about something rolling without slipping, we could have tried to do this thing a little bit harder way by figuring out what's the acceleration from Newton's second law. Well, the quick way to do that would be to figure out what alpha is for the instantaneous rotation about this, contact point. And then I know that will give me what the acceleration of the center mass is perpendicular. This stuff here was the radial. This will be the transverse part. The part that we called tangential. And if I look at the forces here, the force of friction is there. It's not 0. It comes in. It actually could be calculated. It just doesn't do any work. It does come in to net force equals ma on this thing, and you could calculate it. After you found alpha by a torque calculation, where you didn't need to involve that because the famous thing, you did it around a certain point where there was no torque due to the friction force. That's a neat little story. Then, that would be a harder way you could do this instead of the shortcut of energy conservation. In problem 8, I just thought it was fun to take Epstein's example from his famous little book, Thinking Physics, to just remind you, you can go faster than you can swim. You've got a certain amount of energy that you generate with your muscles. And in thinking about whether you're running or swimming, you certainly got the momentum, that you get is equal and opposite to the momentum of the ground or of the water. But what's different is the kinetic energy. The kinetic energy that goes into the earth is zero, into the ground is zero. The kinetic energy that goes into the water is kind of comparable to the kinetic energy that you get from all of it. And the way you quickly see it is, I've got a little story here and in my solutions where, you can look at work and you can say, well, the earth doesn't move, so there's no work on it, so therefore no delta K on it. Whereas the handfuls of water that you're moving or kicking around, do move. And so there is some kinetic energy, that makes sense, put into them. But there is one little thing I wanted to say. I said it here, but let me do it this way. Kinetic energy is 1/2 mv squared. That's 1/2. Let me multiply and divide by m. I get m squared v squared over m. And this is another form that you'll see over and over again. P squared over 2m. That's also equivalent to 1/2 mv squared. Well, if the p is the same, but there's an m here, you can see how for the Earth, with the huge m of the Earth or the ground, that's negligible. But the mass of the water, the local water, the water that's close to you that you're disturbing, you're not moving the whole swimming pool, is smaller, and the kinetic energy therefore associated with the water is much bigger.